Welcome back to ECE 340. In a week, you will have exam number 3 at this time. Before that, you need to complete homework number 7, which is due today, and homework 8, which is due the next time we meet. So you have the weekend to do homework 8. And because of that, we're going to be, I hope, are there seat belts in these chairs? You may need to fasten your seat belts. We're going to try to slide or really go through this material quickly today, and then we may sort of catch our breath Tuesday, but you'll have to do quite a bit on your own in chapter 6, I think is what I'm saying. But I'm hoping that you've seen Fourier series before. We will have a review session. The ECE 530 room was open at that time on Wednesday at 5 o'clock. It wasn't on Tuesday. For that reason, we'll have it the day before or the night before the exam is scheduled. So the review session is a week from, well, not a week from, it's next Wednesday at 5 o'clock, and I will try to record that, and the key word there is try. So we'll see how well that happens. Today what we want to do is get into Fourier series. I'll try to motivate that, provide an overview, and hopefully we will start to figure out how do we construct a trigonometric Fourier series. How do we build it up? And hopefully that will become a little bit more clear as we go. Here's where we're going to start. The motivation. If I gave you the following signal, x of t, and I said, okay, low-pass filter this particular waveform, and this waveform is always on. It's been going since t equal minus infinity, and it continues for t going to infinity. This is infinite of duration, in duration, and it's periodic. I have indicated the period. The period is 2 pi, not pi. You have to figure out when's the first time that this starts repeating. That's now a period of 2 pi, and if I now gave you this signal x of t and said, okay, push this through or apply this to a low-pass filter, what would you expect as the output? Do you have any feel for what this might do? Any insight, any intuition as to what might happen? And maybe I think I didn't do a fair enough job. Let's just say that's a 1. So now we have to remember what we have. X of t is the signal, isn't it? X of t is our signal, and the low-pass filter is our system. And we are injecting that signal into a system, and we want to know, how do those two things play together? Do they play nice? Are they mean to each other? What's happening with respect to h? H of t is the impulse response of this system, which is a low-pass filter, and x of t is this basically periodic sequence of pulses, and those pulses are of duration in time 3.14. And was Pi Day over spring break? I hope you enjoyed Pi Day. Whenever 3.14. All right. Now, could you do this based on the tools that you now have in your box of tools in this class? What's the brute force way that you could figure out y of t? Convolution. You could do the convolution problem, couldn't you? If somebody gave you a low-pass filter, you could find that system's impulse response, h of t, and you could convolve that h of t, and what's an impulse response of a low-pass filter look like? It might, and now this is for the benefit of those in the class and not listening to this, but the h of t might have some exponential behavior. That's a low-pass filter, and depending on the bandwidth of that filter, that's going to influence the steepness of that exponential decay. Now, you just told me the brute force answer is to do the convolution. But we want to be able to maybe intuitively think through what the answer in the back of the book will be. And a lot of times you can get by with an answer like this in terms of it depends. Well, what does it depend on? It depends on the cutoff frequency of your filter. I didn't specify the bandwidth of this low-pass filter relative to your signal x of t. And we'll need to know that. That's the question you would probably want to ask. What is the cutoff frequency of the low-pass filter, capital H of S, if you were designing a low-pass filter? And you guys know how to design low-pass filters. Yes? Especially Butterworth, low-pass filters. You can populate those poles in the complex S-plane. You know their angular separation given a particular order, and the order will depend on your mood, the day of the week. The order depends on the specification, doesn't it? How fast do you want to roll off, and how sharply do you want that to happen? How steep do you want that transition band from the pass band into the stop band? Let's suppose that the cutoff frequency, and I'm going to scroll through a lot of this. So if you're frantically writing, I'll make these notes available. I don't know about the audio, but the notes will at least be available. I'm wanting you to try to get comfortable with this material and thinking about what's going on. Suppose now we put a cutoff frequency of 1 radian per second on that low-pass filter. Can everyone see the Bode plot? For a low-pass filter, let's say it's first order, just for grins. We have a first-order low-pass filter. What's the transfer function of that if the cutoff frequency is 1 radian per second? 1 over s plus 1, isn't it? We have a DC gain of 1. We have a pole at minus 1. We have 1 over s plus 1. That's the capital H of s. The impulse response, you could simply inverse Laplace transform capital H of s, and you have this e to the minus t. There's your exponential, if you needed to convolve that system. Now, we've figured out what the cutoff frequency is. One of the key ideas to realize is that x of t is periodic. And once it's periodic, then that tells you that you can create a Fourier series representation for that x of t. And a Fourier series representation you can just think of as a bunch of sines and cosines added together, with the additional information that their frequencies are very intimately related to each other. But once I give you a sine wave or a cosine wave, once I give you a sinusoid and a transfer function, can you now tell me what's going to happen at the output without going through all the convolution? If I walked up, all right, this will jog your memory. If I walk up to the system and I start hitting it with a sine wave, what's going to happen? You know what's going to happen, right? You'll get a sine wave out, and that sine wave will be at the same frequency that you're exciting it with. If you have a linear time invariant system, you have an H of S, a capital H of S. You know the behavior. All you have to do with capital H of S is do what? Figure out what it's doing to you, right, as a complex number. You evaluate h of j omega, whatever I was shaking, whatever the input frequency. So given any sinusoid, you can give me the sinusoidal steady state component associated with that sinusoid. Is it clear what I'm saying? Let's now figure out what the frequency content of a periodic waveform is, and in this case, x of t. We can figure out from its period, and in x of t's case, that period was 2 pi long. That now gives us this information for determining the fundamental frequency. That's 2 pi over cap t, 2 pi over the period. And that's not very fast. For a signal that repeats every 2 pi seconds, every 6.28 seconds, that's pretty slow, isn't it? As far as a periodic waveform, and it's on half the time. It has a duty cycle of 50%. Now we know what the fundamental is. The harmonic content is going to be related to this fundamental frequency, and the harmonic content is just integer power or integer multiples of this fundamental. We will have frequencies of 1 radian per second possible for this periodic waveform. We have 2 radians per second as a frequency, 3, 4, 5. All of those are possible frequencies for the harmonic content. What's the second harmonic, potentially? 2 radians per second. The third harmonic is 3 times the fundamental. If I change the fundamental, if omega naught was 6, and now I said, what's the second harmonic? It's going to be 12 radians per second. The third harmonic is 18. So you know the harmonic content in the fundamental given the period of the signal x of t. Now what I did is I just put this into MATLAB. Now that we have this information, x of t, we know that it has a period of 2 pi, and it's a square wave. And I believe in this case, I have it going from 0 to 1 as far as a value. Then I said, you know what, I want to really make this a powerful filter. So I created a 10th order low-pass filter, and I went ahead and just left my cutoff frequency at 10. But we know if it's Butterworth, we're still only going to be down minus 3 dB at 10. I'm sorry, at 1. What did I say? Did I say 10? 10 to the 0, which is 1. I want a cutoff frequency of 1 radian per second. So that cutoff frequency is right at the fundamental frequency of my excitation of that periodic waveform. What do I know about the second harmonic? How is it going to be impacted as it passes through this system? Here's the first harmonic, isn't it? That's at 1, or that's the fundamental. The second harmonic is right here at 2. How will that be impacted? Here's our second harmonic. If we have a second harmonic component in x of t, we'll have to figure out if we do or not, but if we do, that's going to be at 2. And it's going to be attenuated, isn't it? Quite a bit. More than 50 dB of attenuation. Pardon? It's probably 60 dB or 70 dB, but I said more attenuation than 50. So now if it follows our rates that we've been using, then we have 6 dB per octave, don't we? And 2 is an octave above 1. We have 10 of those in terms of our order. So it's 6 dB per order of our filter. That means we have 60 dB of attenuation. And what is 60 dB of attenuation in absolute sense? You have minus 60 is equal to 20 log of some gain, m. Isn't that 1,000? That's a reduction of 1,000, 0.001. Somebody can double check me. But now your second component will be amplified by 0.001 as it passes through that low-pass filter. That's quite a bit of attenuation. Relative to the first component, or the fundamental, which is only going to be changed by 0.707, or 1 over the square root of 2, 3 dB. This is now what would happen if you ran the convolution problem. It would take a while for your system to respond to that sinusoidal input. Obviously, my x of t wasn't going from minus infinity all the way to plus infinity. I had a transient. And you could tell me how big the transient was going to be in terms of duration. But in this case, we reached steady state after about, let's say, 18 seconds, for example. And you could compare that with the input. The input is the green, and the output is the dashed blue line. And now what do we see at the output? We basically see the first harmonic, don't we? A sinusoid in the sinusoidal steady state. And that's the intuitive behavior that I would hope that you would start to think about possibly happening, but it all depends on the bandwidth or the cutoff frequency of your low-pass filter. And here's the MATLAB code to produce all of that. If you wanted to know where your 10 roots were, there they are. And I had a bandwidth of 1, so those, if we did the absolute value of those, better give us a magnitude of 1. Should I have a real pole? I had a 10th order filter. It's even, so I would not expect to have a pure real pole in this case, and I don't. That's now the MATLAB code. Here's basically a summary of what we did. H of S was a low-pass filter. X of t was periodic. That means boom. Once we've identified we have a periodic waveform, we can find the Fourier series. That simply means that we have this collection of sines and cosines. X we could write as a sum of sinusoids. Here's a picture, and this is what you'll need to be doing for the homework. You'll be needing to draw these line spectra. What are the component parts for each of the different harmonics? What are the coefficients that scale the sines and cosine terms? This is the compact trigonometric form, and I don't know if these lines really are representative of that. I just put some in. The DC value is probably okay. That was a 1/2. I could visually see that. But what did we have in the sinusoidal steady state? We have a DC offset. That was it blue, the blue dashed line. Whoa, that was quite a ways back. That's a little bit above 0, isn't it? So we do have a DC offset, and now it's oscillating up and down around that DC offset. What did we do? We filtered that. So effectively, so what have we done? To get into an intuitive feel for what's happening, we went into the frequency domain. Somebody drew this picture of x of t. That was the time domain waveform. But then we said, oh, if we find its Fourier series, now we can figure out its frequency information. We can go into the frequency domain. And once we have our signal understood in the frequency domain, then we can start to compare that with the frequency response of our system. For an ideal low-pass filter with a cutoff frequency of 1, I've exaggerated that. Now I said let's go ahead and assume that it's including the fundamental. Now we are including the DC and the fundamental with our low-pass filter. And if you wanted to just keep a particular frequency, maybe you would pass this x of t through a bandpass filter that only pulled off the third harmonic. And then you would need to design a bandpass filter that isolated on that frequency that you're wanting to capture, the third harmonic. If I said design a bandpass filter to pass the second through the fourth harmonic, or I might say design a bandpass filter that has a bandpass interval from 1.5 radians per second up to 4.5 radians per second, you now know what the output will be in the sinusoidal steady state. You would just then isolate on those second, third, and fourth harmonics for that periodic waveform. That's what you should be starting to get comfortable with in talking about signals and systems. We can look at it in the time domain, we can look at it in the frequency domain. We can look at it both ways and hopefully gain some insight. Here are some key ideas about the Fourier series. One is, once you have a periodic waveform, we know it has a Fourier series. Yes?
Before you continue, how fast did you set up to sample the signal?
So in terms of the MATLAB simulation, I didn't even think about it. I just picked a sampling rate or a sampling interval of 0.001. And I can hopefully, that's fast enough relative to this 2 pi periodic waveform. Because really I would want to probably sample that 60 times maybe in that one period. And so I would divide 2 pi by 60, and that gives me 1/10, right? So 0.1 would be a sampling rate that might work, and I exceeded that by a factor of 100. But that's where I just said, I don't want to worry about it, I'll just pick a fast one. And it wasn't too extravagant. It wasn't 10 to the minus 12. So I don't have a lot of data points, but I have a fair number. But MATLAB, I'll let it do the number crunching for me. Does that answer your question? And that should be in the MATLAB code. I scrolled through that very quickly, but that's in there. And that will be a part of your notes, or these notes. If we're dealing with Fourier series, what's the first thing you want to do? Is my signal periodic? If x of t is not periodic, you're not going to be using the Fourier series analysis approach. Okay? So we need to figure out, is your signal periodic? If it is, now we can continue. If it's periodic, the first thing you'll want to do is identify the period. That's one of the key things, is figure out what's the first time that this waveform starts to repeat itself. Periodic means x of t, little t, is equal to x of little t plus capital T. And I might call that capital T sub 0, just to be the fundamental period. Hopefully I'll be, and maybe I should here, since I use omega 0, maybe I should say, let's call that T sub 0. I now know what the fundamental frequency is, either in hertz, f sub 0, or in radians per second, omega naught. And I know that I could potentially have harmonic content in that periodic signal at integer multiples of that fundamental. They don't have to be there, but they could. You're not going to have any other frequencies present. So once you've identified the period, now you know what possibly you could have. The others are not going to happen. Frequencies other than the fundamental and its harmonics. So if you had the A above middle C, 440 hertz, then if you went an octave above that, there's your factor of 2, you would be at 880 for the next A. And in this class, we're always working with A's, aren't we? Well, that's the goal. All right. So if I gave you a periodic waveform, and it could look pretty messy, you are now trying to figure out what's my period. And once you have that period, and if I want to be consistent, then I should call this T sub naught. Notice the period is not just this triangle piece. It also includes this negative piece in this particular example. And then it starts repeating. You simply need to figure out what is my interval defining the period. And now you know the fundamental frequency and all of the harmonics that are potentially there. Now, here's something that maybe you already know, but if you don't, keep it in mind. If I gave you a generic sum of sinusoids, and all these sinusoids are periodic individually, is their sum periodic? And I give you the answer. But you're not guaranteed that it is. That's maybe not so intuitive. So if I gave you 4 sinusoids, and I added them up, and I said, okay, here's a signal, x of t, and you go, and I say, is that signal periodic? You're going to go, I don't know, it depends. I'll have to check. And what are you going to check? Well, you'll check section 6.1-3. This is a hint. If you're reading this weekend and you want to do some of these problems and they start asking you, is this signal periodic? Is this signal periodic, which might be a sum of 2 or 3 sinusoids? What you're looking for is you find the frequencies in each of those pieces. You take their ratios, pairwise. And if all of those pairwise ratios are rational, then you have a periodic waveform. And all of that is based on the fact that you are looking to have x of t equal to x of t plus t sub 0. The fact that you can now find a capital T sub 0 where this starts to repeat, that then will dictate that this ratio of frequencies is rational. That's where this little test comes from. Okay? So if I give you cosine of 3 pi t, and then I give you cosine of 6 pi t, and sum them up, is that periodic? Yes, because 3 pi over 6 pi gives me 1/2, or 3 over 6. That's rational. But if I gave you something a little more ornery and said cosine of the square root of 2t plus sine of t, that's never going to repeat, is it? It's going to be just something that you can never find an interval of time where that will start to repeat again. That's the reasoning behind the ratio of the frequencies being rational. Is that clear? That's one of your homework problems, is figuring out, given a signal, is it periodic? And what's good about that signal being periodic? You can do the Fourier series on it. If you can't, then what would you do? Well, you would just look at each of the pieces that make up x of t, and you know what the sinusoidal steady state response will be for each of those pieces. Maybe you can't do the Fourier series, but you can still find the frequency response or the sinusoidal steady state response from each of those frequencies if you have a linear time invariant system. Now, once we have identified that we have a periodic waveform, the next key thing in Fourier series is to figure out how much of each harmonic we have. How much of the fundamental do we have? Do we have the fundamental piece? Is it there? And that the formulas for that, for the different kinds of Fourier series, are included in table 6.1 on page 599. There's a column that tells you how to compute these coefficients or these weights, and we'll try to get through an example. I think we will. But then you might end up with different components for the different harmonics, and this is now called, maybe obviously enough, a line spectra. You now have frequency content only at these specific frequencies, where these frequencies are the harmonics related to omega naught. And the harmonic content at the second harmonic is given by the amplitude c sub 2. This is now in the compact trigonometric form, which is different from the trigonometric Fourier series, and that's what we'll talk about, which is different from the exponential, but the frequency content will be consistent. We'll just have slightly different coefficients to worry about. Now, if I said, suppose your fundamental is 10 hertz. Well, no, 10 radians per second. Let's keep it in radians per second. Let's say your fundamental is omega naught is 10 radians per second. And I say, pass this waveform. Let's just say that we don't have any more c's beyond c sub 4, that all the other pieces, all the other harmonics are 0. If I now say, pass this signal, x of t, through a bandpass filter that has a frequency interval of 22 radians per second up to 39 radians per second, what would you say is the sinusoidal steady state output? Or what are you going to see in the sinusoidal steady state? You'll just see the third harmonic, right? You're now filtering between 22 and 39. You're only going to pull off that third harmonic. And if you knew what this value was, c sub 3, and you knew what your system response was at 30 radians per second, h of j 30, you could figure out what your sinusoidal steady state response would be. This is then the compact trigonometric form for the Fourier series. You have an amplitude or a magnitude, and you have a phase or an angle. That's the frequency information or the frequency content of your waveform x of t. And that plays with what? The system that signal is being applied to. Signals and systems. That's this course. That's the second key piece. The first key piece is my signal periodic and find its period. The second, find these pieces, the component parts. The third key idea is to convert, or you should be able to convert between a trigonometric Fourier series, a compact trigonometric series, and an exponential Fourier series. And you know how to do this. This is just algebra. Trigonometric involves sines and cosines in your Fourier series expansion. The compact trigonometric converts those sines and cosines that are at the same frequency into just a cosine. And you know how to combine sines and cosines at the same frequency, or you need to. That's how you would go from trigonometric to compact trigonometric. And this table, 6.1, gives you the formulas. If you find the A's and the B's in the trigonometric Fourier series, you can compute the coefficients and the phase in the other two, the compact trigonometric or the exponential. The exponential is related by Euler to the compact trigonometric or the trigonometric. You know how to use Euler and how it's related to sine and cosine. Cosine of x equals e to the jx plus e to the minus jx over 2. Now you know what you're going to see. When you get exponential, now you have positive and negative frequencies. There's nothing scary about negative frequencies. It just helps us with the math. So it's fine to have negative frequencies. If you have a positive frequency at 2 radians per second, if you're now describing that by means of the exponential Fourier series, you're going to have something at minus 2. All right, now we can start, well, one more thing. Let me just reiterate what some of the benefits of the Fourier series provide. Couple of advantages. One, the Fourier series allows us to understand the bandwidth of our signal, what frequencies are there, and, well, that's sort of the same thing, bandwidth and frequency content. Which frequencies are there? How wide maybe is your signal, and what frequencies are in that width of frequency interval? Once you know that you have a periodic waveform, maybe the bandwidth of your signal is infinite in extent, but maybe beyond 20 radians per second, it's negligible. So realistically, maybe all you have to worry about are the components between DC and 20 radians per second. That will be evident from your coefficients that make up the Fourier series. Here's the second advantage, and that's the trash can advantage, isn't it? If you excite a system, a linear time invariant system with a sinusoid, you know that output is going to be at the same frequency. It will just be modified by how that system passes that frequency at that particular frequency. How does it change its magnitude and its angle? Questions? So that was kind of a quick ride through Fourier series, but I think that will give you the background for some of the homework. Now let's see if we can actually compute or figure out what the Fourier series might look like. How do we find a Fourier series? There's 3 different varieties that we can find. We could do the trigonometric, and that's a lot of times the easiest to think about by hand calculation, except you have to integrate sines and cosines, and sometimes that gets a little ugly. Compact, usually you get the trigonometric and then you convert sines and cosines to a cosine. And we could also do the exponential Fourier series. And we'll try to do a couple of examples with trigonometric and exponential. I don't know if we'll get to both of those today. All right, let's look at the general form then for a trigonometric Fourier series. A Fourier series, as I have already indicated, is just a collection or a combination of sines and cosines. We could have a DC offset. That's going to be called a sub 0. Then we will have a sub 1 that scales cosine at the fundamental, omega naught t. Then we will have a second cosine term, possibly, at the second harmonic, and that will have a coefficient a sub 2. Then we just keep repeating that pattern. The third harmonic, its coefficient, we will just call a sub 3. Yes, sir?
How far are the harmonics go? That just dictated these.
So the question was, how far do we go relative to these coefficients? How many a subs do we compute? Sometimes you can actually compute it for a sub n, where n is a variable. Then you have all infinite number of the a sub n's. Sometimes you have to maybe do it individually. Then I would suggest, and I think on the homework, I have you actually have MATLAB compute some of these integrals for you. And you can do that with your calculator also. Your TI-89s or the Inspires will integrate for you, just like MATLAB, and you can do it symbolically. Then you might do 3 of the non-zero. MATLAB's doing it for you. Hopefully you don't have to do too much heavy lifting. You can let MATLAB do the heavy lifting. It's nice to know the DC offset and a few of these A's. And in the trigonometric Fourier series, not only do you have cosines, that just keeps going with the cosines, but you also have sines. You have B1 sine, and that's at the fundamental, plus B sub 2 sine 2 omega naught t, plus, and that just keeps going. Where omega naught, that's 2 pi over T naught, where T naught is the period that you now have identified for your waveform x of t. Questions on that definition? This is just the definition of the trigonometric Fourier series. What we have to figure out is how do we find the A's and the B's? Okay, how do we compute those? Yes? So the question was, why do we not have a phase shift in these sines and cosine arguments? Is that correct? We will have phase shifts in the argument of the cosine when we take and compute the compact trigonometric Fourier series. We have essentially a phase shift because we now have a cosine and a sine at the same frequency. That's giving us our angle. And the angular information then is really contained in the relative relationship between the A sub n's and the B sub n's. But in this formulation, you don't see the angle explicitly. It's only when you convert these cosines and sines into a cosine. You put those two pieces that are orthogonal to each other together into a cosine, and now that gives you a phase shift in the argument. And that will be the compact trigonometric form. This one's maybe easier to compute by hand because you don't have to worry about that angle. You just have to worry about sines and cosines. And the nice thing is that the cosine and the sine are orthogonal waveforms. Is it clear when I say they're orthogonal waveforms? If you multiplied them together and integrated over one period, what happens? Nothing happens, right? They cancel. They're orthogonal. It's like if you looked at x and y and took their inner product, what's going to happen? They're orthogonal. Nothing. That's what the sine and cosine do. And the nice thing, too, also, is that cosine omega naught t and cosine of 2 omega naught t are orthogonal. You're building this up. So if you can now find A1, you've now extracted all the information you need that's your x of t aligns with the cosine at your fundamental. That's what these A's and B's mean. It sort of gives you how much of this cosine omega naught t is in your original waveform x of t. You could make this a little bit easier to write down if you use the summation formulation. You can now say, oh, this is plus sum from n equal 1 to infinity of a sub n cosine of n omega naught t plus this sum, let's say, from m equal 1 to infinity of b sub m sine of m omega naught t. hopefully it's clear if I call this the right-hand side that you initially said that x of t was periodic. Well, now that right-hand side is also periodic, and so you haven't violated the fact that x of t is periodic. The right-hand side is preserving that information also. You have now kept this signal as a periodic waveform, and again, the period of that waveform is simply t naught, which is 2 pi over omega naught. Maybe you're not used to seeing it in that form, so if you're not, then write it the way that you're used to seeing it and say that omega naught is this 2 pi over f naught, which is 2 pi over t naught, and that's what you will remember until you retire, right? Omega is 2 pi f, and f is 1 over t. This is what you will remember. And t naught is the smallest time interval such that x of t is equal to x of t plus t naught. Now that we've defined the trigonometric Fourier series structure, let's figure out how to find some of those a's and b's. And one fact that we will use over and over again is the fact that these pieces that make up x of t, each of those pieces are orthogonal to all the other pieces. That's going to play a big role in this computation of the coefficients, the a's and the b's. How does one determine a sub n's and the b sub n's? Let's just do it gradually. Let's start with the very first one. Let's look at a sub 0. And now, what does a sub 0 represent? That's the DC offset, or that's the average value of x of t. You might be able to get that by inspection. On the exam, if somebody gives you an x of t, you might be able to say, oh, by inspection, a sub 0 looks like it's 1/3, or maybe it's 5. Maybe you can see it by just looking at the average value of that x of t. And now, how do you find the average of a waveform? You just integrate it over the interval, the period, and divide by the period. That gives you your average. And if we plug that into the definition for x and integrate the expression, we'll see that that's what falls out. What are we doing? We're trying to find the average value of x of t. And x of t, defined relative to this complex defined by this trigonometric Fourier series, is a sub 0 plus this sum of a sub n cosine of n omega naught t plus the sum from m equal 1 to infinity of b sub m sine of m omega naught t. What we want to do now is try to find a sub 0. Well, if we integrate all of these terms over one period, and just pick the period that's easiest for you to integrate with respect to, what's going to happen? If this is getting too confusing, an integral and a summation, this is what you put on your t-shirt, right, and walk around campus with. Integrals and summations, and then people go, huh? If it's not making sense, just look at the first few terms of that summation and see what's happened. You're now integrating a cosine, omega naught t. You're integrating a cosine of 2 omega naught t, just scaled by some coefficient, a sub n, and you're doing the same with the sines and the cosines. What happens, so let's just see what I have. I have now the fundamental. And did I draw that to be a cosine or a sine? This is now a sine, isn't it? So this is now, this would be the sine of omega naught t if this is my period t naught. If I now integrate that over that one period, I hope it's clear that you have the same amount of area underneath the positive as you do the negative. What if we integrated the second harmonic piece? Now this is going to really get... That's supposed to be a sine wave. That's twice the frequency as the first one. This is still t naught, but now I have this area and that area better be the same as those two areas. And if I just keep going, if I went to the third harmonic, I now have 3 bumps, 4 bumps, 5 bumps. The cosine is the same way. I have the equal amount of positive area as negative area. That allows me then to go back up here and do what? Say that all of these terms vanish. All of these terms vanish. And now I'm simply left with the integral of x of t dt over 1 period is equal to the integral of a sub 0 dt over 1 period. But what was a sub 0? That was constant, and you know how to integrate a constant. Don't you wish your math teacher would have given you that problem on the final? Maybe they did. You're here, right? So you've successfully completed your calculus, which is good. So you know how to integrate a constant. That's just a naught little t, and we evaluate it over 1 period. That's going to be a sub 0 t naught. And now we can solve for a naught. This now says that we now have a formula for a naught. That's 1 over t naught, the integral of x of t dt over 1 period. And that's why you took your calculus, is so you could take this class. All right, one of the reasons. You can now find the average value of a waveform, x of t, by integrating it over 1 interval, period, and dividing by that period. That's a naught. What about the other a's and b's? Let's look at a1. Since we had so much fun doing a naught, let's look at a1. Here is our expression. Well, maybe it's getting clouded there, but if we come back here, here is our defining expression for the trigonometric Fourier series. Now what I'm going to do is I'm going to use some ideas that I know about sines and cosines, and in particular, when they are squared. What happens if I square a cosine? Let's say I have cosine of t and I square it. Can you rewrite that as another expression? Cosine squared of t is equal to 1 minus sine squared. Yes, that's not quite what I wanted, but that's true. But what I wanted to do was write it in terms of, get rid of the square, is what I was wanting to do. So I want to get rid of the square because that's ugly. I can't integrate a square. So I want to now find another formula. Do you remember 1/2 plus 1/2 cosine of 2t, where we double up that frequency? And now what do we have? Now we have a constant and something that has twice the frequency. And that's going to magically go away when we integrate over one period, isn't it? That's what we want to play on. And the fact that cosine squared plus sine squared, that's our joke, isn't it? But that now allows us to convert these cosines squared and sine squareds into something that looks like a DC plus twice the frequency, which is good. We need to know that. What we're going to do now then, to make that happen, in order to find a sub 1, let's now multiply. Remember what a sub 1 was scaling. A sub 1 was scaling the first harmonic, or the fundamental. So let's multiply the entire definition of x of t by whatever a sub 1 was scaling, which was the cosine of omega naught t. So let's now multiply the definition by the cosine of omega naught t, and again integrate over one period. What does that do for us? Well, we said we would take x of t and multiply it by cosine omega naught t. We're going to have a sub 0. We're going to multiply that by cosine omega naught t. We're going to take, and now hopefully you can see my carriage return. I'm hitting a carriage return and I'm still on the right hand side, but I now have a1 cosine omega naught t, but I'm multiplying that by another cosine omega naught t. And I have an a sub 2 cosine 2 omega naught t times a cosine omega naught t. And I can just keep doing that, right? But I also have to remember my b's. I have a b1 sine of omega naught t times cosine omega naught t, plus a b sub 2 sine 2 omega naught t cosine omega naught t, and I could just keep going. All I've done so far is multiplied my definition of the trigonometric Fourier series by cosine omega naught t, where cosine omega naught t was what was scaled by a sub 1, because I'm trying to find a sub 1. This is the nice part that I wanted. This is now my cosine squared of omega naught t. But now what I want to do is I want to integrate all these terms. I integrate this over t naught. I integrate this over t naught. I integrate this over one period. All of these I now integrate over one period. Let's go back to the first one. The left-hand side, I'm just going to have to compute. This is going to be, and whoops, I forgot my dt's, didn't I? So this is now dt, dt, dt. That first piece on the left-hand side, I'm going to have to compute that. How does x align with cosine omega naught t? How is it correlated? That's going to be a value. That will be a number. How does x align with cosine omega naught t? Now, what happens with this first term on the right? What happens to this first term on the right? What's a naught? That's a constant, isn't it? So I can pull that out of the integral. And now what am I doing? You're integrating cosine over one period, and what did we just say that was going to do? That's going to go away. This piece is gone, isn't it? Now we have to remember our trigonometric relationships. What's the cosine of A times cosine of B? A product of two cosines. And that's in chapter B of your book, if you forget. Right? It's at the very end of chapter B. Is that like cosine of A minus B plus cosine A plus B? It's basically the sum and difference of these arguments, isn't it? Now, if I take the cosine of the difference, what do I have? Cosine omega naught t. And what's the integral of that? That's 0. What about the sum of those two arguments? That's cosine of 3 omega naught t. That's going to go away. So this piece is gone. What about the sine and times a cosine? Again, that's a sum and difference of the arguments. And in this case, I have, what do I have? I think this one boils down to sine of A minus B plus or minus sine of A plus B. Sine of 0, 0. Sine of their sum, sine of 2 omega naught, that's going to go away when I integrate. This piece now is gone, as is all of these other higher ones. The only piece that I have left on the right-hand side is that cosine squared piece. And what are we going to do with the cosine squared? So now what we're left with is we have this integral of x of t cosine of omega naught t dt equaling this integral of cosine squared omega naught t dt, and this was a sub 1 over t naught. What we want to do is now rewrite this as 1/2 plus 1/2 cosine of 2 omega naught t. Is that looking okay? What happens when I look at the second half of that? That goes away, doesn't it? And all I'm left with is that 1/2. So that now I have the following. I have on the right-hand side, I have this integral of a1 times 1/2 dt. This guy, when integrated, 1/2 cosine 2 omega naught doesn't go to 0, but integrated it does. Is that clear what I'm trying to state? But now I integrate this over t naught. But what is that? That's again the integral of a constant, isn't it? So that's now a1 over 2 times t naught, which is equal to this integral of x of t cosine omega naught t dt over t naught. And I can now solve that for a sub 1. I now have a sub 1 is equal to 2 over t naught integral over t naught x of t cosine omega naught t dt. Now you can continue to do this and you will find that you will get general expressions for the a's and the b's. You can do this. So if you wanted a sub 2, you will now multiply x of t times cosine of 2 omega naught t and find that expression and then scale it by 2 over t naught, and that will give you a sub 2. A sub 3 is the same structure. that means then that in general, to find the coefficients, to find the a's and the b's, a sub 0 was just the average value, wasn't it? We had 1 over t naught integral of x of t dt over t naught. That was the average value of x. If you continued to look at finding the different a sub n's, you would find that they have the same kind of structure we just found for a sub 1. That will be x of t times the cosine of the appropriate harmonic frequency dt. So let's say that's n not equal to 0 and n greater than or equal to 1. And that is basically asking, how is x aligned with the different harmonic cosine pieces? Similarly, we could find the b's. The b sub m's are 2 over t naught integral over t naught x of t sine of m omega naught t dt. If I now ask you to find the trigonometric Fourier series, is it clear how to do it? Let's try to work an example, or at least get started. Was there a question?
Yeah, if it's periodic from X, are we guaranteed that Fourier series converges?
So now if we have a periodic waveform x of t, we are going to assume that the Fourier series converges. Yes. So that now what we want to do is, let's look at an example to see if we can make this even more clear if it's not clear just yet. Suppose that I give you the following waveform. Here's x of t, and let's say that I have an amplitude of A, and this is probably not drawn very accurately, but let me now label this. Let's say that this is now t naught over 4 minus t naught over 4. This is now t naught. This is 3 t naught over 4. This is minus 3 t naught over 4, and this is minus t naught. And these extend in both the positive and negative time direction. This is now my periodic waveform. It's a pulse train of amplitude A, and it's on between, well, it's even, isn't it? And that will have different ramifications on the A's and the B's. But let's just go through and not worry so much about that. I'm not going to get all hung up on, oh, it's even. You should know that you have certain coefficients and not. I just want you to understand how to approach the problem and to create some of the solutions. Do you expect to have an A sub 0? What does A sub 0 represent? Remind yourself what that is. That's the average value or the mean of x of t. Does this have an average value, this waveform? Now you're having to look and see, do I have an equal area under or above my horizontal line, or is some more of it on top or more of it on bottom? In this case, I have nothing down below, do I? So you would expect it's going to have a positive average value. And in fact, it's only on half the time, right? So you can I hope, kind of guess what the average value is going to be. A over 2. Let's just see if that's what it is. From our formula, let's just make sure that our formula is correct. We said that A sub 0 is 1 over T naught integral T naught x of t dt. And that is now 1 over T naught integral. It's only non-zero between minus T naught over 4 and T naught over 4. And here you might want to be selective in what time interval you select or choose. Here I'm not going to go from 0 to capital T naught. Why? Because then I have 3 different regions to worry about, and I would have to break my integral up into 3 distinct parts. If I simply look at the period being from minus T naught over 2 to T naught over 2, then I can only have to worry about it being on in one interval. I have to worry about this interval, but that's 0, and this interval, and that's 0 on either side, and that's okay. And it doesn't change across 0, does it? So that now, in that interval, my amplitude is A, it's constant. And this is now dt. And you've now told me how to integrate a constant, because I forgot. This is now A over T naught t from minus T naught over 4 to T naught over 4. Or this is now A over T naught over 4 minus a minus T naught over 4. Doing this as long as we can, right? The T naughts cancel, or maybe I don't want to see that just yet, but what's inside the square bracket? T naught over 4 plus T naught over 4, which is T naught over 2, and that's what I expected for an average value. So my algebra or my calculus verifies my gut, my instinct, my intuition. Yes? And now it's okay to shift your interval where you're integrating. It doesn't matter which period you select, just pick a period that's convenient for your integration process. Because the waveform keeps going forever, doesn't it? So it's reached a steady state. You just have to worry about one period. Select the period that's the easiest for you. Let's now see if we can compute, and in this case we can actually compute these a sub n's all at once. I can say now, find an infinite number of the a's. And you can go, you're kidding me. I'll be up a few hours tonight. Well, now you can just leave the variable n in there. You now have a sub n is 2 over T naught integral over a period x of t cosine of n omega naught t dt. But that's now going to be this 2 over T naught integral. It's only non-zero between minus T naught over 4 and T naught over 4 with an amplitude of A. And now we simply have to remember how to integrate the cosine. Integral cosine, that's sine, isn't it? And we have to worry about the argument. So that now we have a sub n is equal to 2 over T naught. We divide by n omega naught. And we have sine of n omega naught t. And we want to evaluate that at the lower limit and the upper limit. And a is in there somewhere. So let's make that right there. We okay? Now we have a sub n is equal to 2a over T naught. We have 1 over n omega naught. And we have sine of n omega naught T naught over 4 minus sine of minus n omega naught T naught over 4. And now we have to get a little bit cute with what we know about sines and the relationship between omega naught and T naught. what do we know? We know that omega naught is equal to 2 pi over T naught. That's by definition of T naught, which says that omega naught T naught, which appears in the argument of some of those signs, is 2 pi. Right? So now what do we want? Now we want to put that in there so that we now have, and we also have that sine of minus x is minus sine of x. We can clean this up or combine these two pieces. Is that okay? So that we now have a sub n is equal to 2a over t naught, 1 over n omega naught. We now have a 2 sine of, what do we have here? We have 2 pi, that's omega naught t naught, times n over 4. Is that okay? And we also have out front, what do we have? We have 2 pi in the denominator. And we'll cancel that, and we'll pull this 2 and that 2, and that 2 will come out. All of this boils down to a sub n equaling 2a over n pi sine of n pi over 2, and that's true for n greater than or equal to 1. And those are now my a sub n's. And because my signal was even, your b's are going to be 0. All of your b's will be 0, and you can figure that one out as an exercise. So we'll pick up at that point on Tuesday.